So the topic today is the chapter 6 of Ryder book, as mentioned by the assignment. The name of the chapter is Gravitomagnetism. As we can see clearly from the name, this is the combination of gravito and magnetism, which will describe the gravity plus magnetism. What is the correlation between magnetism and gravity is if any massive particle or massive body is placed in a space and space-time curvature, it rotate or it curves, it create a space-time curve. Same goes to magnetism. When an electric charge, or you can say electron, revolve or move, it create an electric or magnetic field around it. So that is the analogy that we can say that massive particle, massive bodies plus charge moves and create field. That is the most general word we can say, that they create field, because electric field create magnetic field, electric charge create magnetic field, and massive bodies create space-time field or gravitational field. That was the very general introduction to the field or to the chapter. That's why we are talking at the basics of this chapter are the most basic in we can say the most important equation of generally the general relativity is the Einstein equations. Similarly, in this chapter we will write Einstein equation, which is let me write in different color. Our mu nu is equal to, oh sorry, there it should be minus, yeah, minus 1/2 g mu nu r is equal to k t mu nu. Let's name this equation as equation 1. This is the main and one of the most important equation in the field of general relativity, and especially in the field of gravitomagnetism. There are two solutions of this equation. Let's name this equation as Einstein field equation. Yes, there are two solutions. I will name them as different. One is given by the Schwarzschild solution, and one is Kerr solution, and according to their names they are given different, like Schwarzschild solution is called Schwarzschild solution, and the solution given by Kerr is called Kerr solution. This solution is like hypothetical method, given by hypothetical method, or in German as they say that it is Antas solution. And it has a very important equation, which is given by g mu nu is equal to a dt square minus b dr square minus r square. Let me write this curve one on the another page. R square into d theta square plus sine square theta d phi square. This is this equation is, you can see, is having four parts. One is dt, dr, and this d theta and d phi. It is four-dimensional equation, and it is in the spherical polar coordinates. We can clearly see that, yes, because it is in r, theta, and phi. We will discuss it in more detail. It gives the metric of, let's say, space-time. This g mu nu give the metrics of space-time. And one important thing, let me write on the next page, is note that this Schwarzschild solution is time independent. This is time independent, and one more important thing is time independent space-time equation. And that is first point. Second point is that it is static. Let me write something in the previous equation. Yeah, sorry, I cannot go to the previous slide for some reason. Yeah, one more thing is the equation that we have written. Let me write it again. G mu nu, there on the left side there was something ad square minus b dr square. This equation, or this g mu nu, gives a matrix, as I said before, gives a matrix metric which describes the geometry of space-time. That is the one of the most important feature of this Schwarzschild solution, is the one of the most important matrix because it describes the geometry of the space-time. As I said before, I will go to there are two solutions, as I said before. One was Schwarzschild solution and another was Kerr solution. Kerr's solution. Instead of static, this solution is non-static. Let me you write it with a black. Non-static. What I mean by non-static is that this is rotating. Yes, here I mean non-rotating, or yeah, you can say non-rotating. Yes. Let me go to the next slide. There are some experiments done to verify or to check the validity of the Schwarzschild equation. The experiments done was, the first experiment was precession perihelion, and second experiment that was performed to validate the solution of Schwarzschild was bending of light. Yes, if these two solutions are possible, if let's say if these experiments are possible, if these experiments are successful, then Einstein field equations are valid. These experiment will check the validity of Einstein field equation. What experiment was done to verify the Kerr's equation or Kerr's solution was verified by the experiment. There are many experiments, but I will go into detail of one, that is precession of gyroscopes. In process of this, they launched a satellite in 2004. They launched a satellite, and that satellite helped us to understand a new concept, which is known as lens tethering effect. Let me write it in detail in next slide. Effect. What is this? Because this is one of the topic also. Lens tethering effect, and it is a drag force. Let me write in short detail here. It a drag force. Yeah. Let's go to next slide so that we can write this about this lens tethering effect in more details. Okay, so yeah, as I said before, light tethering effect this is let me write in verbally. Let's say when a massive body move in space-time, it create a curvature. Caused by its gravitational field and besides, if it drag, as I said before, it is a drag force drags the space-time, due to which the surrounding objects are affected in such a way that these objects have to follow geodesics. In simple words, I'm not very good in drawing, but let's say there is a heavy object, and this is the space-time curve, or let's say this is our bed sheet, and this is heavy stone. When we rotate this stone, for example, let's see here. When we rotate from here to here, what will happen? This will rotate the space curve, very little part of it also, of the blanket or of the cloth with itself. That is what is called the light-thirring effect in the context of space-time curve. When a heavy object is placed on this space curve, it drags the space-time curve with itself. Yeah. The next concept is about the that is the first topic. This is linear approximation. The important thing in this is the metrics due to gravity. Metric due to gravity. There are some important things that I want to mention before, which I will denote by G nu mu, and which shows the curvature. Second thing is I want to show is the line element, which will be line element, in which we will use denoted by ds square, and this metric due to gravity will be used here, nu into dx nu dx nu. And third thing is weak field limit, which is g mu nu is given by rho and mu nu plus h mu nu. Sorry, mu nu. These two are for general gravitational field, but this is only for the third one is only for the weak field. Here this thing denotes almost nearly flat space. Let me write it, nearly flat space, and this thing is the perturbation, sorry, in the field of or let's say let me delete this one and change it to very small perturbation. What I mean by very small is the value of this h mu nu, or even in the contravariant and covariant, both of them, the value will be very less than 1. The value of this rho is given by a matrix. Rho nu mu is equal to this one, and here is all of them are 0, 4-dimensional matrix, and yes, which is equal to 1 if we see from very far. From a far distance, this value of rho will be is equal to 1. If we consider this thing, then we can clearly mention that. Let me go to the next slide. That g mu nu, as we written in the previous slide, is equal to h mu nu. That is very important result. We will use it almost everywhere. What I mean by that is, even anywhere we see g mu nu is we can put the value of h mu nu. The important thing after this is the Christopher symbol. Let me go into the detail of that. Let me write them with the name connection coefficients, which are given by, generally they are written like this, is equal to 1 by 2 g k gamma g gamma mu nu plus g gamma mu minus g mu gamma. In short notation, normally in mathematics we don't like this kind of long equations or something. We have to make them short. Then we can write them as this thing, because if we write in contravariant form, it looks like something like this. And this thing is, you can see this is derivative with respect to nu, this is respect to mu, this is derivative with respect to gamma. So why not we write them as partial of g? This is the inverse of, that's why I write this thing, is because this is inverse of the upper one. And its value is definitely given by, in our case, like in this case, we give this the value of this term by mu is equal to rho mu minus h mu. If we put this here, let me write it in the next equation, next slide, sorry. Christopher symbol k mu is equal to 1 by 2. This is value of g, as I have written in the previous slide. Rho mu minus h mu. Just now, a few minutes ago, we said that this term is very, very less than 1. This value is very less. Let me write the upper equation completely. In the same way, this was partial, and again there was a value of g mu nu. We will put this value of, but in covariant form. Yes. Let me write this, change this bracket into square bracket here. So this is, we can write this equation as, okay, 1 by 2, if this time the term is less than very, very less than 1, so definitely we can ignore it. Rho mu nu, and this term can be expressed as, in short form, partial h mu. Why? Because I just now in the previous slide I said that this term is equal to 1. Why? Because the reason I give is that from very far distance this rho mu nu looks just like a flat space, which means the value is 1. And when the derivative of 1 is taken, what happened to 1? Derivative of 1, it becomes 0. So only this term is remaining, and that is the perturbation term. Let me write in the short form, 1 by 2 rho mu nu partial h mu. Yes. Yeah, this is this value of we will use this, so that's why. Yeah, these were the topic about the Christoffel symbol or connection coefficient. Now the most important part is the Ricci tensor. We will go to the Ricci tensor, which is the main part of this topic. We know that Ricci tensor is given by, let me write the name, which is, we all know that it is given by You have been doing it in assignments also. Our new mu is equal to mu new partial v plus for sample lambda. Let me write this value so that, and then I will explain it. Minus yes. Okay, I just now explained that this term is combination of this. Okay, I understand that this is one h, which is already small, less than. This is another h. Derivative of very small term multiplied by derivative of another small term, it really less than become 1. Same case goes here. So these two terms can be ignored. Why? Because this is one derivative, this is second derivative of who? Of this h, which this h is really small already. So there is no point of taking this term and this term. That's why we ignore these two terms, and with the remaining terms are only the first two, which are, let me write them here for clarity, partial lambda mu nu minus b lambda. Yeah, so this is the term that we will investigate in more details, yes, in the next slides. Yeah, first step is this one, multiply by derivative. Second step, this finding this and then multiply by this. Let me write their name also. This is first and this is second. As I said in the previous slide, the first step would be to find the Christopher symbol, which is this one, is equal to 1 by 2 rho mu with respect to v plus h rho v with respect to mu minus h with respect to rho. And then as I said before, we have to multiply derivative or partial derivative here. By writing the partial derivative, let me write in different color, partial lambda, and then v is equal to 1 by 2 lambda rho h, sorry, here should be rho mu v lambda plus h v lambda minus h lambda. Let's name this as equation 1. Yeah, that was the first step. Let me do same step as I said before, find the Christopher symbol. Sorry. Second step was to find this Christopher symbol and then multiply with derivative, is equal to 1 by 2 rho mu plus, and let me write this and then I will explain. Sorry, minus h mu rho. Okay, so now the next step is to put the derivative of with respect to v, or with respect to mu, sorry, nu, and then is equal to same thing as upper just keep putting the new term, sorry, plus h minus, yeah, this is equation 2. I'm naming them because we have to use them at the end. Yeah, let me go to the next slide. Here the important we have to put this equation 1 and equation 2 in the value of in the Rickett answer. Okay, if you put the value of equation 1 and equation 2 in Rickett answer, let me write it directly that this is r mu nu is equal to Rickett answer 1 by 2, because all these terms have 1 by 2 terms, and rho h nu and h nu lambda, this is lambda, plus the notes of these can be given yeah, at the end of the lecture. Is kind of long equation, that's why I'm just writing it immediately without just by putting the value of first term, equation first, and equation 1 and equation 2 in the Rickett answer, and that's why it is quite long. Yeah, minus h nu plus nu rho yes, plus all the terms of h that we ignore, but I mean sorry, h squared that we ignore, that I said before that this term, this is 1h, this is 2h, so when these terms are multiplied they become h squared, which is definitely very, very small terms, so definitely we are going to ignore them. Yes, for doing for making our work easier, let me do something fast, that the equation is equal to 1 by 2 this is Laplacian I am putting here, and I will explain the reason later, minus plus these 0h square terms. What I have done is, okay, this term I have contracted this term and this term. Similarly in here I have contracted this term and this term. Similarly here, if you see, I have contracted two terms. One is, sorry, this is lambda, this one, and this one, and this one. Similarly here I have contracted two terms, again one is lambda and one is rho. In the second last one I have contracted rho and lambda. In the last term I have contracted lambda and rho. That's why these two are remaining. Yeah. Yeah, let me, in the book, the next equation, or this is just above equation, above the 6.4 equation. Let me write it in again 1 by 2 h mu lambda. This is, sorry, lambda. I have the habit of writing h as lambda plus h lambda mu lambda minus this Laplacian comes here, minus plus 0 h squared. This is in the book, they have written this as equation 6.4. Sorry. Yeah, and we name it as equation 3 also. What I have done here in here is, you can clearly see here, this and this cancel each other, and this is this one, this term comes here, and this one terms come here. From equation 5.25, which my friend already explained, is if we see the equation of Ricky tensor, which is already explained in very details in the book, is equation 5.25. Sorry, let me write it. Yeah, 5.25 equation. Let me write that equation. Mu nu is equal to k t mu nu minus 1 by 2 g mu nu and t, by putting the value of k. Let me put the value of k is equal to minus 8 pi, also given in the book, c square, and the remaining terms will be same as this one, minus 1 by 2 g t. Yes, I will put all the value of Ricky tensor here, and then this term on the right side. Let me go to the next slide so that we have large space. Yeah, so on the left side we were having Ricky tensor, which is value is h. I wish I could copy that place, but I don't know, for some reason I am unable to copy that. I think we can, sorry, I again write lambda here. Okay, here is h. In one notebook we can copy, but I don't know in PowerPoint. It is, I'm doing in PowerPoint. I am not, I think I need to learn about the one notebook also. Yeah, minus h lambda mu plus 0 h square. On the right side was, I have written it again, h over c square. Yeah, t mu nu minus 1 by 2 t. Yeah, so if we multiply these two on this side of the equation, so the 8 will become 16. I'm not going to write all this left side. Let me write the at the end, c square minus 1 by 2. Sorry, here is no dot. This is not dot. Yeah. So this equation is minus 16 pi h over c square, and this thing in the book they have written it as s mu nu Yes, this is this value. Let me write this term. All this term will come in the same way here also. Yeah, so that is my presentation. Thank you.